Google quantum computer solves a problem in about 3 minutes, a problem that would take the world's fastest supercomputer around 10,000 years, and yet the problem itself was completely useless. No practical application, no business value, nothing you or I could directly use. So why did this useless calculation make global headlines and freak out tech companies, governments, and cybersecurity agencies around the world? Because of how it was solved. It wasn't done on a regular computer like the laptop or phone you're using right now. It was done on a quantum computer, a machine sitting in a fridge colder than outer space, using the rules of quantum mechanics to manipulate the tiniest building blocks of reality. In this video, we're going to break down what a quantum computer actually is, how quantum computers work in plain English, and why they could completely transform our future, or break some of the systems we rely on today. By the end, you'll have a clear, honest understanding of quantum computing. No hype, no magic, just what it really is, and why it matters. Let's rewind to where this all started. It's 1981. At a mansion at MIT, some of the greatest scientific minds of the century gather for the first conference on the physics of computation. You've got legends like Freeman Dyson, John Wheeler, Charlie Bennett, and one person who would change everything, Richard Feynman. Feynman, already a Nobel Prize-winning physicist, stands up and drops a line that basically invents an entire new field on the spot. He says, in essence,
nature isn't classical. If you want to simulate nature, your simulation has to be quantum mechanical.
In other words, every computer we had built so far, from room-sized mainframes to the most powerful supercomputers, was fundamentally the wrong kind of machine to fully model the universe. All of them are classical computers. They work with bits, tiny switches that are either 0 or 1, off or on. Feynman asked a radical question. What if we built a computer that plays by nature's actual rules, the rules of quantum mechanics? To see why that's a big deal, we need a 10-second crash course in what makes quantum mechanics so weird. Imagine a tiny particle trapped in a box. When physicists solve the math for this system, they don't get one simple answer. They get a whole ladder of possible energy levels, like floors in a building. And here's where it gets strange. In quantum mechanics, the particle doesn't have to pick just one floor. It can exist in a superposition, a combination of multiple states at once until you measure it. This isn't just abstract math. This is how real atoms and molecules behave. It's the physics that runs chemistry, materials, and ultimately, everything around you. Feynman's insight was simple and profound. If nature itself uses superposition and other quantum effects, then a truly powerful computer should use them too. A quantum computer wouldn't just simulate nature, it would be built using the same rules. For a while, this was mostly theory. People played with ideas for quantum communication, but nothing that clearly showed, this will crush classical computers. That changed in the early 1990s. Two physicists, David Deutsch and Richard Jassa, came up with a problem where a quantum computer could provably beat any classical computer. The task itself sounded simple, figuring out whether a function is constant or balanced. Using hour, day. But the key is how many times you need to check it. A classical computer might need multiple tries. A quantum computer, using superposition, could solve it in a single shot. This was the first real hint of quantum advantage, a situation where a quantum computer can solve a task faster than any classical machine. But the real earthquake came with a mathematician named Peter Shor. Shor was reviewing papers for a computer science conference when he came across work by Daniel Simon that many reviewers thought was pointless, useless math. Reject it. Shor saw something different. Simon's algorithm could find hidden patterns in functions, what mathematicians call periods. Shor realized that many hard problems could be reframed as period-finding problems, and one of those problems is factoring large numbers into primes. That sounds boring. Until you realize that modern encryption, the stuff protecting your credit card, your messages, government secrets, depends on how hard it is for classical computers to factor enormous numbers. For regular computers, cracking that encryption would take millions of years. Shor showed that a sufficiently powerful quantum computer running his algorithm could do it in hours or days. That got the attention of intelligence agencies instantly. The NSA actually questioned him about his work. Overnight, quantum computing went from fun physics idea to potential threat to global security. A race for quantum supremacy had begun. But you can't just snap your fingers and build a quantum computer capable of running Shor's algorithm. First, you need to know what a quantum computer physically looks like. Physicist David DiVincenzo laid out a set of criteria. You need good quantum bits, qubits, that you can initialize, control precisely, entangle with each other, and measure reliably, all while preserving their fragile quantum states long enough to do useful work. Unlike a regular bit that is either 0 or 1, a qubit can be in a superposition of 0 and 1 at the same time. A nice analogy is a coin. A classical bit is like a coin lying flat. It's either heads or tails. A qubit is like a coin spinning in the air. It's not just heads or tails until you catch it and look. Now add another layer of weirdness. Quantum entanglement. What exactly is quantum entanglement, and why is it so crucial for quantum computing? Imagine you have two coins that are magically linked. When you finally catch and look at one and it lands heads, the other instantly becomes tails, no matter how far apart they are. That's the rough intuition behind entanglement. In quantum computers, entanglement creates correlations between qubits that are fundamentally impossible in classical systems. With multiple entangled qubits, the quantum state of the entire system becomes incredibly rich and complex. So complex that classical computers can't even fully simulate what's happening for anything but tiny systems. This is the secret sauce behind the power of quantum computing. A classical computer with 10 bits can only be in one of 1024 possible states at any instant. A quantum computer with 10 entangled qubits exists in a superposition of all 1024 states at once. As you add qubits, the number of possible states grows exponentially. But there's a brutal catch. Quantum states are insanely fragile. Any unwanted interaction with the environment, heat, vibrations, stray electromagnetic fields, can destroy the delicate quantum properties that give these computers their power. It's like trying to balance a pencil on its tip while someone's shaking the table. That's why quantum computers look like giant golden chandeliers hanging inside enormous refrigerators. Google's Sycamore processor, the machine behind that 3-minute versus 10,000-year result, operates just a few thousandths of a degree above absolute zero, colder than deep space. The entire system is isolated from noise as much as possible just to keep the qubits quantum for a tiny fraction of a second. And even with all that, current quantum computers are incredibly error-prone. Today's devices might make an error in roughly 1 out of every 1,000 operations. Classical computers, by comparison, might make an error once in every billion operations. Because of this, modern quantum processors are often called NISQ devices, noisy intermediate-scale quantum computers. They have tens or maybe hundreds of qubits, but they're noisy and limited. So why did Google's 2019 demonstration still matter so much? They programmed their 53-qubit Sycamore processor to perform a very specific task, sampling from a complicated quantum probability distribution, essentially generating random numbers according to a very particular pattern that arises naturally from the quantum behavior of the device. On paper, that sounds trivial. Who cares about fancy random numbers? But simulating that same quantum process on a classical supercomputer is brutally hard. According to Google's estimates, Sycamore did it in about 200 seconds. They claim the world's most powerful classical supercomputer, Summit, would need about 10,000 years to match it. IBM later pushed back and argued that with clever tricks and better algorithms, you might do it on a classical machine in days instead of millennia. But even that more conservative estimate still represents a huge quantum advantage for that particular task. The key point isn't that the task itself changes your life. It doesn't. The significance lies in the level of control. We've now built quantum systems with enough qubits, enough coherence time, and enough precision in their operations to beat classical machines at some well-defined problems. That brings us to where quantum computing actually is today. We're in the NISQ era. Quantum computers with dozens or hundreds of qubits exist, but they're noisy, limited, and not yet ready to crack your bank account or instantly revolutionize everything. Think of them like the room-sized classical computers of the 1940s. Impressive, important, but still very early. Different companies are betting on different hardware approaches. IBM and Google use superconducting circuits. IonQ and others use trapped ions. Some are exploring neutral atoms, photons, or exotic topological qubits that might be naturally protected from certain types of errors. The holy grail is fault-tolerant quantum computing. Machines with built-in quantum error correction that can run complex algorithms for hours or days without falling apart. To get there, we'll probably need millions of physical qubits working together to create maybe thousands of stable, logical qubits. The ones that actually run algorithms like Shor's at useful scales. That sounds distant, and it is. But even before we reach full fault tolerance, we're already exploring real use cases. In optimization, quantum algorithms might help design better supply chains, financial portfolios, or traffic systems. In machine learning, hybrid quantum classical models could uncover patterns in data that are hard for classical models alone. In quantum simulation, early quantum computers can already start modeling small molecules and materials in ways that push beyond what classical computers can do. Drug discovery companies are experimenting with quantum computers to simulate molecular interactions more accurately. Financial firms are testing quantum methods for risk analysis and portfolio optimization. Materials scientists are building quantum simulators to probe exotic phases of matter that are almost impossible to study with classical tools. Nobody agrees on the exact timeline. Some experts think we'll see commercially useful, application-specific quantum computers within the next decade. Others argue that full, general-purpose, fault-tolerant quantum computers might take several decades, but the debate is no longer about whether quantum computers are possible in principle. It's about how fast we can solve some brutally hard engineering problems. If we succeed, the implications go far beyond faster computers. Quantum computers could revolutionize drug discovery by simulating large molecules and protein interactions that are completely out of reach for classical machines. They could attack optimization problems in logistics, energy, and transportation, making global systems more efficient and less wasteful. They could help design new materials, better batteries, superconductors, or something we haven't even imagined yet. At the same time, there are real risks. A powerful quantum computer running Shor's algorithm could break much of today's public key cryptography. That's why there's a parallel race to develop and deploy quantum-resistant encryption, new cryptographic schemes that remain secure, even in a world with large quantum computers. And then there's the science side. Many of the deepest questions in physics about black holes, high-temperature superconductors, and quantum many-body systems involve calculations that explode in complexity on classical computers. Quantum computers might finally give us the tools to explore those questions directly, using one quantum system to simulate another. So what even is a quantum computer? It's not a magic box that makes everything fast. It's a very specific kind of machine that uses superposition, entanglement, and interference to process information in ways classical computers simply can't. For some problems, that will make quantum computers unimaginably powerful. For others, classical computers, and AI running on them, will remain the best tool. We're still at the beginning of this story. From Feynman's insight in 1981 to Google's quantum advantage experiment in 2019, we've gone from an idea on a chalkboard to real, if imperfect, quantum hardware. The quantum computers of today are primitive compared to what might exist in a few decades, but they're our first serious attempt to harness the fundamental strangeness of quantum mechanics for computation. In a universe that runs on quantum rules, it might be inevitable that our most powerful computers become quantum too. The race is on to build the first truly useful, fault-tolerant quantum computer. Whoever gets there first won't just win a scientific contest. They could reshape technology, security, science, and the global economy. The quantum revolution has started, and whether you ever touch a quantum computer directly or not, its impact will ripple through the tools, the networks, and the AI systems you use every day. Subscribe for future tech breakthroughs, comment quantum to join.